There are three common phases of matter, or states. There's solids, liquids, and gases. These are all around us and are so common we don't even really think about them or their properties. A gas is characterized by its low density, the fact that it has no fixed volume, and that it has no fixed shape. This means that a gas will expand to fill whatever container it's in.
The explanation of this behavior is found by considering how the particles are arranged and how they are moving. This is described as part of the kinetic theory of matter. This theory states that all matter is made up of particles, and that these particles are in constant motion. Now for a gas, these particles are far apart, separate, and moving independent of each other. The particles of a substance that exists as a gas at room temperature have such a low attraction for each other that they do not stick together. In fact, we will often assume that there is no attraction at all. In this simulation, we see particles moving about, hitting each other and hitting the walls of the container. They move in straight paths, only changing direction because of a collision. Some particles are moving faster, some are slower, but they all have kinetic energy. Because of the variety of particle velocities, we will often refer to the average kinetic energy of the particles.
In order to fully describe a gas, we need to identify certain parameters of the sample that we're looking at. These include the number of particles, the volume, the temperature, and the pressure of the gas.
What is volume? Well, straightforward enough. It is just the space that a gas occupies. The SI unit of volume is the cubic decimeter. The volume could be represented by a cube that measures 1 decimeter by 1 decimeter by 1 decimeter. A decimeter is equal to 10 centimeters, and so this cube is also 10 by 10 by 10 centimeters, or 1,000 cubic centimeters. There are several conversions related to volume shown here that are pretty handy to remember, including the fact that the SI unit cubic decimeter is the same volume as the metric unit liter. Likewise, a cubic centimeter, also referred to as cc's, is the same as a milliliter. Temperature is defined as the measure of the average kinetic energy of the particles. Remember that we speak of an average since all the particles are moving at a different velocity. In SI, we use the Kelvin scale, a scale that is based upon absolute zero. You may be familiar with the metric Celsius scale. The Celsius scale is based upon the freezing point and boiling point of water. The convenient thing about the two scales is that the unit of Kelvin temperature, the Kelvin, and the size of the degrees Celsius are the same. This means that the conversion from one to the other is just a matter of adding or subtracting 273. In the simulation, you can once again see that these particles are moving at a variety of velocities, but overall have an average kinetic energy. The Kelvin temperature is the measure of the average kinetic energy. If heat is added to the gas sample, the particles begin to move faster. Their average velocity increases, and so the average kinetic energy of the gas particles increases. The temperature is therefore higher. Now there's something else I want to show you. Different gases have particles of different mass. This is actually why gases have different densities. Helium and methane gases are less dense than air, and so will rise or float. There are also other gases that are more dense than air, and so will sink. This is not the only difference. When two different gases are at the same temperature, their particles have the same average kinetic energy. This simulation is depicting the movement of relatively massive particles. If I switch the view to show less massive particles, you will see that they are moving, on average, at a higher velocity. Please note, however, that the two samples have the same average kinetic energy as represented by the fact that they are at the same temperature.
We are born into a sea of gas. We are surrounded by air that includes nitrogen, oxygen, and other trace gases that are constantly striking us, exerting a force per area that is known as air pressure.
Pressure is defined as a force exerted over a certain area. The SI unit of pressure is the Pascal. A Pascal is equivalent to a force of 1 Newton exerted over an area of 1 square meter. The more particles that are present will result in more collisions. More collisions mean a greater force exerted over the area, and so the pressure would increase. Just to put this unit of pressure in perspective, the unit of pressure that the air is exerting on you is approximately 101,000 pascals, or 101 kilopascals. Looking again at our simulation, if an intergalactic space penguin, or ISP, were to materialize in the middle of our gas, those gas particles would hit the penguin's surface. The ISP would experience an atmospheric pressure. There are several other units of pressure, some of which you have heard of or worked with before. These include ATM, the unit atmosphere, millimeters of mercury, or pounds per square inch, PSI. In conclusion, let's take a look at how the different parameters will affect each other, particularly how do they affect pressure. By increasing the amount of gas in a container, as stated before, there will be more collisions, and therefore a higher pressure. It does not matter what the gas is. Doubling the number of particles will double the pressure. Increasing the temperature means that the particles are moving faster. Faster moving particles will collide with the walls or any other object's surface more frequently and with a greater force. This results in a higher pressure. Finally, decreasing the space that the gas occupies will cause the particles to collide with the walls more frequently and raise the pressure. Particles are not moving faster, they just have less distance to travel before they hit the walls. So that in a nutshell are the definitions of the gas and the parameters that we use to describe them, all through the lens of the kinetic theory of matter. We will save the explanation of the existence of ISPs for another video.